Hey guys, welcome back to another video. In this video again, we're going to solve a few hard questions from physical chemistry, that is of A2 level chemistry, and we're going to solve from equilibria and stoichiometry related questions. So I've already made one video and I'll link that in the description for you to watch. And starting off with March 19 paper, variant 4.2. So this is part B of some question, and it is saying when chlorine dissolves in water, the following reaction takes place. So you have your chlorine reacting with water, forming HClO, releasing H plus ions and releasing chloride ions. Fair enough. When solutions of chlorine are used for water purification, the pH of the solution of the chlorine is kept near pH 7 by the addition of a base. Fair enough. Chlorine is dissolved in water to produce 1000 cm³ or 1 dm³ of a solution containing 0.17 moles of HClO and 0.17 moles of HCl. Okay, a buffer solution is then prepared by adding 0.2 moles of NaOH to this solution. The NaOH reacts initially with HCl. Calculate the pH of the buffer solution. Okay, so they've given you a bunch of information. They're telling you that chlorine will dissolve in water to release these acids, right? This is HCl. And now, since HCl fully dissociates, it's going to release exactly 0.17 moles of H plus ions. Okay. So they're asking you what is the ultimate pH of the solution. To figure that out, you need to know the ultimate concentration of H plus ions in the solution. How are you going to do that? Let's see. First, I need to understand that since they've said they're adding 0.2 moles of NaOH, what's happening to the NaOH? Is it ultimately affecting our equilibrium, right? Is it affecting our H plus concentration? Let's see. So since they've mentioned that firstly, the NaOH is going to react with HCl. So let's see what sort of reaction takes place and what is our leftover amount of H plus. So if you have 0.2 moles of NaOH, it is going to go through neutralization reaction with HCl, right? So 0.2 reacts with 0.17 moles of H plus ions of HCl. And it is going to neutralize all of this acid, right? It is going to neutralize all of those 0.17 moles of H plus ions. And what's going to happen is it's going to form NaCl, right? NaCl and H2O. So it's neutralizing your 0.17 moles of H plus ions. Now, after the reaction has taken place, you're still left with 0.03 moles of NaOH. Right? Since 0.17 was left of HCl, was there of HCl, the rest of the NaOH, since the reaction is 1:1, NaOH plus HCl, this reaction is 1:1, hence a certain amount of NaOH will be left. And that turns out to be 0.03 moles of NaOH. Now this leftover 0.03 moles of NaOH will then react with another acid that is also present in the equilibrium in your solution. That is HClO, right? HClO. It's going to react with HClO. And again, neutralization reaction will take place, neutralizing only 0.3 moles of HClO. Why? Because this is the limiting reagent now. Your base or alkali is now the limiting reagent. Hence, it will only neutralize 0.03 moles of HClO. Now, after 0.03 moles of HClO has been reacted, what is your leftover amount of acid? That is going to be 0.17, your initial moles of HClO, minus 0.03, right? Minus 0.03. Because this is the amount that has been reacted to form H2O and NaClO, right? Both of those, salt and water. So now you're left with 0.14 moles of your HClO acid. Great. Now, in the solution, what you now have is NaCl, right? This is salt solution. And you also have NaClO, which is 0.03 moles. Hence, if you just remove this Na, chlorate ions exist in the solution with a moles of 0.03. It has 0.03 moles because reaction took place between NaOH and HClO, where 0.03 moles of HClO reacted, leaving in the equilibrium 0.03 moles of chlorate ion. And mind you, this chlorate ion is going to act as our base. So, ultimately what's going to happen is this 0.14 mole of HClO that has not reacted will dissociate and release H plus ions in the presence of chlorate ions, which is a salt, which is a base basically, your salt base, that is NaClO. But since it is going to ionize, it's going to exist as chlorate ions, that is Cl minus ions, which acts as a base. So I can now write an equilibrium equation between my salt, acid, and your H plus ions, right? So I know the dissociation constant of HClO that is given to us over here, since it's a weak acid, and it is given as 2.9 into 10 to the power of minus 8, and that is going to be equal to your H plus concentration that you need to find out times 0.03 of those ClO ions that is produced by the acid plus base reaction. Acid, weak acid plus NaOH base reaction. So there is 0.03 moles of the ClO ions left. Fair enough. Now you may ask that why am I not converting this into concentration? The reason is the volume is actually 1000 cm cube, which is why if you divide this by 1, it's still going to be 0.03. So it doesn't matter. Anyways, so your acid remaining is actually 0.14 as according to this calculation. So I know the acid concentration, I know the base concentration, and I also know my dissociation constant. Hence, I can find out the concentration of H plus ions, right? Okay. Fair enough. So now you can directly find out your concentration of H plus ions. So calculate for H, and the concentration is going to be 1.35 into 10 to the power of minus 7. Great. Now when you calculate the pH, it's going to be minus log of this H plus concentration, and it's going to be 6.9. Beautiful. Now notice one thing. In the question, they had mentioned that they want to keep the pH of the buffer solution around the pH of 7. And ultimately, your answer does resonate with that, right? So we know our answer is correct. Fair enough. It isn't that complicated, but fairly complicated, since you need to consider 2 steps. One reacts with HCl, next reacts with HClO. Then also consider that some will be left and dissociate in the presence of ClO ions, which acts as a base. So that is how you find out the H plus concentration and that is how you're going to find out your pH of the solution. Fair enough. That is your question 6. Now, question 7 from summer 23 and paper 4.1. This is some part E of some question of this paper. And what is it saying? It is saying that number of moles of water of crystallization in a hydrated ionic salt can be determined by the titration using aqueous EDTA ions with a suitable indicator. So they want you to find out the water of crystallization of a hydrated ionic salt by using aqueous EDTA ions. Fair enough. Which is an indicator. Fair enough. So how much of the hydrated chromium sulfate do you have? The salt. You have 0.255 grams of hydrated chromium sulfate salt. Fair enough. And this is your formula of your salt. That is chromium 2 sulfate 3 and n moles of or n portions of H2O. Great. It is now dissolved in water and made up to 100 cm³ in a volumetric flask. Now, of the 100 cm³, only 25 cm³ of this solution is taken, and it requires 26.2 volume of 0.008 mole per dm³ concentration of EDTA ions, which is the indicator. So you need this much of the indicator to, I guess, oxidize or reduce or something. To go through ligand exchange reaction. Anyways, yeah. So to go through the ligand exchange reaction, you're going to need these many moles. If you multiply it, you're going to get the moles. So you need these many moles of aqueous EDTA, right? So you need to find out how many moles are required and how many moles are present in this 25 cm³ of the salt solution. That is your chromium sulfate, right? Fair enough. So the reaction that occurs is shown, that is a ligand exchange reaction. Use the data to calculate the value of N in the formula of this salt. So ultimately, after all the calculation, they want you to find out how much of or how many portions of water molecules are there present in your hydrous salt. So they want you to find the sort of the empirical formula, right? Now, to be able to do that, I first need to understand how many moles are reacting in the 25 cm³, right? Okay, so let's figure that out. For the 0.255 grams over here, that was first made into 100 cm³, and that 100 cm³, from that 100 cm³, you only took 25 cm³. And it is found out by multiplying the volume times the concentration. If you convert the volume into dm³, it's going to be 0.0262. And if you multiply the volume with concentration, the moles of EDTA turns out to be 2.096 into 10 to the power of -4. That is the moles of EDTA or indicator you need to go through ligand exchange reaction with 25 cm³ of the solution, of the salt solution. Hence, if I need these many moles of EDTA to convert how many moles of your hydrous chromium ions, you will need exactly 2.096 into 10 to the power of -4 moles, right? Why, you ask? Because the ratio is 1:1. So if these many moles were required to turn this into this, you exactly will turn 2.096 into 10 to the power -4 moles of hydrous chromium ions, right? So since the ratio is 1:1, whatever the mole of EDTA you find, is also going to be the moles of your hydrous chromium ions. Fair enough. So you know the mole of chromium ions. Now find out the total mole of chromium ions in your total 100 cm³ of the solution. That is going to be, since 100 divided by 25 is 4, you're going to multiply whatever moles you got over here, over this, right? Whatever you get over there, you're going to multiply with 4, right? So this multiplied by 4 turns out to be 8.384 into 10 to the power of minus 4 moles of EDTA, right? Or moles of chromium ions, either you can say. So what you have over here is 8.384 into 10 to the power of minus 4 mole of Cr2 SO4 3 NH2O. Okay. So you have a total of these many moles of chromium. Okay. Now listen carefully. That is 8.384 into 10 to the power minus 4 is the total number of moles. But remember one thing. Over here there are 2 portions of chromium. So to be able to find out how much or what portion of H2O there is, I need to convert this mole of chromium to 1 portion of chromium ion. Right now, this 8.38 is representing 2 portions of chromium ions. But I need to convert that into 1 portion of chromium ion such that I can find the empirical formula. Okay. So, for 100 cm³, you need 8.38, fair enough. So, the moles of 2 portions of chromium ions is 8.384 into 10 to the power minus 4. Hence, with respect to 1 portion of chromium ion, it is going to be 4.192 into 10 to the power of minus 4, right? So you're dividing this by 2. Okay, so that is the amount in moles with respect to 1 portion of chromium ion, right? If you remember from A's, that is how we find out the empirical formula, and that is exactly the logic I'm using over here. Now I know with respect to 1 portion of chromium ion, what is the mole going to be. Now let's find out the moles of sulfate ion in the solution, in the hydrated solvent, I mean. So it's basically going to be this times 3, because with respect to 1 portion of chromium ion, chromium 3 plus ion, there is 2 portion of chromium ion, and there is 3 portion of sulfate ion, and there is n portion of water molecule. Again, I'll repeat. With respect to 1 portion of chromium ion, there is 2 portion of chromium, there is 3 portion of sulfate, and 10 portion of water. Hence, I can say the moles of sulfate is going to be 1 portion of chromium times 3, right? Times 3. Or you could directly do this as well, times 3 by 2, that works as well. Due to 2:3 ratio, so it becomes 3 by 2 times whatever the moles you get. That is this. Anyways, you can multiply this with 3 as well to get your moles of sulfate ions. And your ultimate moles of sulfate ion is going to be 1.257 or 1.258 into 10 to the power minus 3 moles of sulfate. Keep that in mind. Now, I'm going to find out the mass of sulfate, the mass of chromium in the entire compound. I know the total mass of the compound, right? I know the total mass. Now, I know the moles of either of the ions. So I can subtract the mass of the ions from the compound to find the mass of water. And then I'll be able to find out the total portions or ratio of water molecules. So let's do that. What is the total mass of both ions going to be? It's going to be basically 52 is going to be most likely your mass MR of chromium. I don't really know. Let me check. Yep, 52 is the mass of chromium. And this is your total moles of chromium. Remember, now I'm finding the mass, right? So I'm going to use the total moles of chromium present in the compound. And the total moles is 8.384 with respect to 2 moles of or 2 portions of chromium ion being present, right? So that is your total moles of chromium ion. So multiply to find the mass of chromium. And now find the mass of sulfate. So that is going to be sulfate has an MR of 96 times your moles. That is what you found over here. And if you sum all of it up, it's going to be 0.16433. That is your mass with respect to both the ions, chromium and sulfate. Now, I know from the question that the mass of the total salt, is it a salt? Yeah, ionic salt. So, mass of the total salt is going to be 0.255, right? So, since the total mass is 0.255, I know the mass of both the ions. So, let's subtract that. And if I subtract it, I get the mass of 0.0907. And that is going to be your mass of water present in the compound. Now find the moles of water present. That is going to be 0.0907 divided by MR. That is 18. And my final answer, that is moles of H2O present, is 5.037 into 10 to the power of minus 3. That is your moles of H2O present. Now, to find the ratio, what are you going to do? You're going to divide that mole with the smallest mole. That is 4.19 into 10 to the power of minus 4. So you're dividing the moles of H2O by the mole of the smallest value. That is 4.19 into 10 to the power minus 4. That is, I'm finding with respect to one chromium ion, one portion of chromium ion, how many portions of H2O there is. With respect to one portion of chromium ion, there is 3 moles of sulfate and there is 2 moles of chromium. So with respect to 1 mole of chromium, how many moles of water is there present, right? So it's going to be 5.037 into 10 to the power of minus 3 divided by 4.19 into 10 to the power minus 4. And that turns out to be 12, right? Over here, notice one thing. If you had gotten a value that was not a whole number, you can already guess that your calculation was probably wrong, right? Anyways, so we get 12, which is the right answer. And basically, over here, what you're applying is the empirical formula calculation, nothing else, right? Okay, now this part, let's see. A solution of chromium aqueous and a solution of Fe3 plus have different colors. Okay, this is not needed for now. This is from transition metals. So that is your question 7. Now for question 8, it is from March 22, variant 4.2. What is it saying? Iron is found naturally in compounds in many different oxidation states. Iodide ions react with acidified H2O2, hydrogen peroxide, to form iodine and water. This reaction mixture is shaken with cyclohexane to extract the iodine. Okay, cyclohexane is immiscible with water. Identify the role of H2O2 in this reaction with iodide ions in acidic conditions. Write an ionic equation for the reaction. This is easy. The role is oxidizing agent because it is going from -1 to 0. So yeah, this equation, you can take a look at it. It goes from 2I minus reacts with H2O2. This is going to oxidize the I minus to iodine and form 2H2O, right, to balance the equation. Fair enough. Since they have said acidified, you're going to consider 2H plus as well. Okay. Okay, that is easy. Now, part 2, was it saying 15 cm cube of C6H12 cyclohexane is shaken with 20 cm cube of an aqueous solution containing I2. That is aqueous meaning water solution. That is, there is water. I mean, I2, that is iodine dissolved in water. And you have iodine dissolved with C6H12. Okay. Now, this reaction mixture is kept until no further change is seen, and it is found that 0.39 grams of iodine is extracted into the cyclohexane. So initially the aqueous solution had all the iodine, and after the equilibrium has been established, 0.39 grams of iodine has been extracted in the cyclohexane solvent. The partition coefficient of I2 between both is 93.8, and calculate the mass of I2 that remains in the aqueous layer. So this is the amount that has been extracted into the C6H12 cyclohexane. So now this calculation is somewhat easy. You know the volume of both, that is volume of cyclohexane, you know the volume of iodine as well, right? So you can find the concentration easily. How, you ask? So basically, you have the partition coefficient between cyclohexane on top and water in the denominator, because that is how they've given your question. Where is it? Yeah, between C6H12 and water. So whatever they mentioned first, put that in the numerator. So I2, concentration of I2 in C6H12 by concentration of I2 in aqueous solution. That is water. So now find the concentration of I2 in C6H12. That is going to be 0.39 grams of I2 divided by 0.015, that is volume of C6H12. Now divided by whatever is left, that is going to be, did they mention how many grams of I2 was initially mixed? No, they did not. So you're going to consider it as X. So basically 0.39 divided by 0.015 divided by X divided by the volume of what? Volume of iodine in aqueous solution. So the aqueous solution volume they've given as 20 cm cube. So if you convert that into dm cube, it's going to be 0.02. So if you put the reciprocal value of this, it's going to be 0.02 divided by X. Now simply make X the subject, and you're going to get the grams of, why is my grams so small? Anyways, so you're going to get the grams of I2 left in your aqueous solution. So if you make this X the subject, that is your grams of iodine left in your aqueous solution. So it turns out to be very small, and it is going to be 5.54 into 10 to the power of minus 3. Okay, so one thing you can understand is iodine is covalently bonded, right? I2, it's a covalent molecule, and it is going to dissolve more in your organic solvent compared to a polar solvent. We already know that H2O is a polar solvent, right? O has negative charge, partial negative, H has partial positive. Now, we have organic solvents like cyclohexane, for example. It is going to do a better job at dissolving non-polar compounds like I2. It is not polar, right? So, that is exactly what, based on, you're going to answer the next question. Okay? So, they're asking you, suggest how the Kbc value of iodine between hexane 2-on CH3 CH2 thrice CO CH3. That is hexane 2-on, and water compares to the value given in A2. Now, when you see the structure of cyclohexane, remember this is not benzene, right? So this is going to have hydrogen, 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 and all that. C6H12, right? So notice this molecule, cyclohexane, is actually quite non-polar. The electronegativity of carbon and hydrogen is quite similar. Hence, it's not as polar. Great. Now, when you bring in a substance like hexane 2-on, what this has is an oxygen atom, right? Now, over here, it only has C and H. It's a hydrocarbon. Now, with a ketone, you have oxygen present, which is a more electronegative atom, which is why this becomes slightly more polar. It is still relatively not that polar. However, due to the existence of oxygen atom, it gets a bit more polar, which is why the advantage that cyclohexane had compared to water is going to decrease. Cyclohexane was very non-polar. Now, compared to that, your ketone is not as non-polar. It is slightly polar. So it's going to do a worse job at extracting iodine. So that is how you're going to answer this question. You're going to say hexane 2-on is polar, while cyclohexane is non-polar. And iodine, being a non-polar covalent compound, does not dissolve in polar solvents. Hence, your partition coefficient will decrease. Because yes, hexane 2-on is a worse solvent for iodine molecule, that is covalently bonded molecules or non-polar molecules, due to its polar part, that is oxygen atom. So due to its polar nature, it's going to act as a worse solvent. Hence, your partition coefficient decreases. Because now H2O has a greater chance of absorbing or keeping I2 absorbed, that is iodine absorbed, right? Since the difference between absorbing capability is not that high, right? So that is how you would answer question question 1 from March 22 paper. And yeah, let's move on to the next question. This is winter 22 paper 4.2, and this is question 4 from that paper. And what's it saying? So yeah, question 4. The value of the solubility product Ksp of iron 3 hydroxide is given by the following expression. So the Ksp is given of iron 3 hydroxide. So iron has an oxidation state of 3+, and OH in the Ksp is going to have a power of what? 3. So that is your Ksp given, and calculate the solubility of iron hydroxide in water. So consider X to be the moles of FeOH3. So with respect to X moles of FeOH3, you're going to have X moles of Fe3+ ions, and you're going to have 3x moles of OH ions, right? You do 3 times X is going to be 3x, right? So you have X moles of Fe3+ and 3x moles of OH. Take that into account. X moles of Fe, 3x moles of OH. Now OH will have a what? Power of 3. Why? Because of the Ksp formula, right? So with respect to your Ksp formula, the OH will have a power of 3. Now, a lot of people often make this mistake of not multiplying X or concentration with 3 and just putting a power 3 over here. That is going to give you a wrong answer, because your concentration actually varies due to the molar ratio between your cation and anion. So you have to consider that the concentration of the hydroxide is thrice as much as the iron concentration. So yeah, that is going to affect your KSP. Okay, so this part is easy. Now you're basically going to make x the subject, that is x to the power 4, and 3 to the power 3 is 37. Make x the subject, and the value of x is going to be what is it going to be? Let me figure this out once again. So it's going to be 2 into 10 to the power of minus 39 divided by 27 cube root, fourth root. Okay, so it's going to be 9.28 into 10 to the power minus 11. Fair enough. Okay, so now part 2, they're telling you the solubility of iron hydroxide in 0.01 mole per dm cube of barium hydroxide. What? Oh, calculate the solubility of iron hydroxide in 0.01 mole per dm cube of barium hydroxide. So initially, you're just considering the solubility of iron hydroxide in water. No other reagents or no other salts or salt, no other basically compound is there in your solution. So you only have iron hydroxide, right? So when you're going to add another compound, let's say NaCl, NaOH, anything, literally, what's going to happen is that is going to hinder or affect the solubility of your iron 3 oxide, right? Whatever solution you add, if there is a common ion between both the what are these alkalis? Between both the alkalis, it is going to affect the solubility due to the common ion effect. So if you already have a concentration of barium hydroxide, that is BaOH2, and now you add Fe or iron hydroxide into the solution, there is already a common ion over here, right? There is already OH ions, right? There is already OH ions. Now, what do you know about the KSP? Since there is a large amount of OH already present in the solution, you would be unable to dissolve as much of the iron hydroxide alkali or iron hydroxide compound due to already the existence of OH ions. Hence, your equilibrium shifts to your left hand side since there is already so much of the product, right? So due to higher amount of hydroxide ions, your equilibrium shifts to the left hand side, and it is going to cause precipitation of iron 3 oxide. So you're going to see iron 3 hydroxide precipitate in the barium hydroxide solution, right? If you add the same amount of iron 3 hydroxide. So now they're asking you, what is the solubility of iron 3 hydroxide in the new solution where there is already a common ion present? Let's calculate. How do we calculate? The concentration of OH ions present in this solution is going to be twice 0.01. Why? Because if there is 0.01 of barium hydroxide, that means there is 2 times the concentration or 2 times the mole. It is going to be 0.02, right? 0.02 mole per dm cube. So the concentration of OH present is 0.02. Great. So now you need to find the concentration of iron that is going to dissolve, right? So if I find out the concentration of iron that is going to dissolve, I'll also get to know that in what amount or what concentration of this alkali or this compound will dissolve, since it is FeOH3. So whatever the concentration of Fe dissolves, the same concentration of iron hydroxide dissolves. It's going to be the same, since with respect to the mole of compound, the mole of Fe is 1:1. Right? But with respect to the mole of compound, the mole of OH is 3. So 3:1. Right? So let's find out the concentration of Fe. How will we do that? We know the solubility. Right? We know the solubility, that is 2 into 10 to the power of minus 39. And that is going to be equal to your X, that is the solubility of Fe that we are going to find out, and times 0.02 to the power of 3. So you're going to find out the solubility of your iron. Right? Fair enough. I have basically plugged in the solubility product into this equation, and I'm asking this equation, what is the concentration of Fe3 plus that will dissolve with respect to already the existence of OH ions. So this is your concentration of OH ions to the power of 3 due to the equation formula. And now you know the concentration of Fe3 plus or iron that is going to dissolve. So this is the concentration of which iron will dissolve, and this is also the concentration of which your iron hydroxide will dissolve. Fair enough. So that is your concentration of iron 3 hydroxide that dissolves into your new solution of barium hydroxide. Okay, so the final answer is actually going to be 2.5 into 10 to the power of minus 34, but I don't know why I wrote 35 over here. I just pre-checked. Anyways, so the final answer of the solubility of iron hydroxide in barium hydroxide solution is going to be 2.5 into 10 to the power of minus 34. And what is this effect called? Common ion effect. Very simple. Rest of the questions are easy. Moving on to the last part. This is easy as well. You just have to find out the moles of the acid left after the reaction is taking place, and using that you're going to find the pH. I've already done something like that somewhere above. Over here. So this is actually a better question to try. Question 6. So yeah, that is question 9, and the last question for this video, question 10. This is basically stoichiometry, nothing else. This is asking you, I don't remember which question this is, which paper it is. If I find it, I'm going to add it in the description. So this is saying most naturally occurring samples of iron 2 oxide, right, iron 2 oxide are found as mineral, what is this? Mineral wustite. I don't know what this is. Wustite has formula Fe20OX. It contains both iron 2 plus and iron 3 plus. 90% of the iron is present as iron 2 plus and 10% is present as iron 3 plus. Deduce the value of X. Now, you have this Fe20 OX. They're asking you, what is the what is the formula of this compound? That is, what are the moles of oxygen present in this compound, right? So how are you going to find that? They've given you the clue. That is, 90% of the iron that is present has an oxidation state of what? Fe2 plus, right? Fe2 plus. And 10% has Fe3 plus oxidation state. Now notice, I have to take into account, since this is not a charged compound, it does not have a charge, the net charge is 0. So the number of oxygen atoms that will be present in this compound has to provide the same charge but negative compared to the positive charge of this compound. So if I need to find that out, I need to say that 90% of the iron is Fe2 plus, hence 90% of 20 is actually 18, right? So 18 ions is going to have a plus 2 charge. So 18 times 2, that is plus 2 charge, is going to give me a plus 36 charge. Then the rest is going to be plus 3 charge. That is 10%, which is 2. So yeah, 20 minus 18, 2. So 2 of the iron ions are plus 3. So plus 3 times 2 is going to be positive 6. So what is the net charge? Net positive charge? 42. Positive 42. Now this positive 42 of charge has to be nullified by the oxygen's negative charge, right? By oxygen's oxidation state. So it's basically going to be, since each oxygen atom has a minus 2 charge, I can say 42 divided by minus 2 is going to be the number of oxygen atoms present. So it is going to be 21 oxygen atoms. So do the calculation yourself now, since it had plus 42 charge, and now you have 21 oxygen atoms with a charge of minus 2, it's going to be minus 42. So fair enough. You have a net charge of 0. So this is how you're going to find out the number of oxygen atoms. Fair enough, that is your question 10, and that is it for this video. See you in the next one.